start this weekend, I guess. Like tonight, I supposed to do 2 more
All right. Okay, let's start lecture. See, I'm not sure why that projector is not working. Okay, so let's just use one projector first, okay, and somebody will come fix it up. Okay, so last lecture, and just a quick review at here what we did in the previous lecture. We talked about a new concept called divergence. Okay, basically this is a definition of a divergence. Okay. You take a surface integral, or you take basically calculate the net flux through this surface S, which is the enclosed surface, okay, and then you divide it by the volume enclosed by this surface S, okay, and then you let this volume go to 0. Okay, so take a ball and let the ball go to 0. Then we get this basically the concept called the net flux over the unit volume, which is divergence. So divergence basically gives us an idea whether it's the sink or source, okay, in terms of the vector field at a certain point. Okay, yeah, and then I think we started and we also covered one example on the divergence theorem. So divergence theorem, basically it's a theorem connecting the double integral and the triple integral together. Okay. So on the left side here you have a double integral. Okay, so this is basically a surface integral over an enclosed surface. First of all, enclosed surface. Okay, so divergence theorem deals with enclosed surface S. Okay, and the enclosed surface S gives a region D. So that's the connection between these two. Okay. Then, if we are going to calculate the net flux through this enclosed surface S, we can calculate as it is. Alternatively, we can calculate this surface integral using a triple integral. So integrate over this region D. The integrand, or what we're integrating, is that divergence, okay, of these vector fields. So divergence, sometimes we call it flux density, right? So you integrate the flux density, then you get the total flux, okay, through that surface S here. Okay, so that's the idea. You integrate the density, then you get the total flux, right? That's divergence theorem. The other thing you have to be very careful with here is, which typically will not happen, but you got to also be aware that this vector field F, okay, this F right here, needs to be continuous, okay, over this region D. Okay, so this F needs to be continuous over the region D. If there's any point inside the region D that actually gives us a singular point, so if that function, for example, is, maybe it's x over x squared plus y squared, or y over x squared plus y squared, for example, right? So that's not a continuous, because it's not continuous at 0, 0 at the origin, right? Then if your D enclosed the D contains the origin, then you actually cannot use this divergence theorem. Is that clear? Yeah. So that's basically, I mean, usually we don't have. I won't give you that type of things, but you need to be aware there is this kind of things here. Okay. And one more thing out here is for divergence theorem. Okay, it's always about our flux. Okay, so our flux. So basically, this means this basically means what? Your n hat, right? The normal vector to the surface S. Okay, this needs to be picked or selected appropriately. Okay, yeah. So if you're giving an enclosed surface, then what is the outward direction n hat? If you're going to calculate this using this divergence theorem. Okay, so that's the idea. The n hat has to be picked correctly. Okay, so let's take a look at one example here. Okay, and then I'll probably show you a little bit more example, but I think we have time here. Okay, so let's look at one example. Here is the vector field. Okay. And the cube, okay, is basically the surface here. So surface S is the 6 sides of the cube. Yeah.
What is the k-hat next?
K-hat.
Yeah, what is the k-hat?
Oh, XZ. Yeah. Yeah. So this is your vector field. Your surface S is the 6th side of this cube at here, and we wanted to calculate outward flux. Okay, so outward flux equal to what? And the cube here, of course, is a unit cube because it's 1, 1, 1 on all sides. Okay, so for this one here, I mean, if you never learned divergence theorem, okay, and if you just go ahead and then carry out the surface integral, so this is enclosed surface, so I'll use this circle right here to indicate. For this particular case, you have an enclosed surface. Yeah. Okay. So if you have never learned divergence theorem, then because I have 1, 2, 3, 4, 5, 6 sides, then if I need to calculate this surface integral, then what do? We basically will calculate 6 surface integrals here, right? Yeah. 6 surface integral, you add them together. Now when you calculate each one of these surface integral S1 to S6, and of course you have to be very clear as which one is S1, for example, which one is S2, right? And so that's has to be labeled correctly. Okay. And now when you do the calculation, then you think back about the approaches that we learned about the surface integral calculation. So basically you need to, okay, I have learned 1, 2, 3, 4 different cases, right, to deal with the surface integral. So in this case here, which case does it belong, right? So we pick the formula appropriately. And in this case here, you have a planes basically parallel to each one of the sides, right? So, and it's the case, if you remember, that's the case what there's a planar case, right? Plane case. Okay. So, and the other thing, if you want to do the calculation, is about outward flux. So each one of the n hat has to be pegged correctly. So I'm just drawing, then this is not that long, right? So for example, for the S1, your n hat will be k hat. For S2, this side here, your n hat will be j hat. Right? So that has to be picked appropriately. And the bottom one here, let's say the bottom one here, what will be the n hat? Negative k hat, right? So that's the idea if you do this surface integral as it is. But now since we learned divergence theorem, so I'm not going to use this approach right here. So I will calculate using the divergence theorem. Okay, so this is what I will use. I'll use the right side of the formula. Okay, so the right side of the formula requires you to calculate del dot f. So let's calculate del dot f first. Let's just basically get it first, and then we'll plug it back into the.
I'm gonna have to come back. I'll look on some stuff.
Sure. No worry. Yeah. So del dot f, and then we'll plug it back to the triple integral. Here's your f at here, right? Del dot f is partial m partial x plus partial n partial y partial p over partial z. Okay, so here's your m, n, p, and that's a pretty simple partial derivative. So you have x, y, here's a y, here is z, here is a x. So you got an x, y plus z plus x, or x plus y plus z. So now I'm going to substitute back into this triple integral. So x plus y plus z, and then dv, right? dv. So dv, this is basically back to the typical triple integral calculation. So you can use dx, dy, dz, or any orders you want, but this is a cube, really it doesn't matter. And because it's a cube, so the x goes from 0 to 1, y goes from 0 to 1, z goes from 0 to 1. So this is a very simple triple integral to calculate. Okay, you can easily get this, which is 3 over 2. Okay. So that's the idea, is basically how to use this divergence theorem, right? Is that good? Yeah. Now, if you are interested in the proving of the divergence theorem, you can take a look at the lecture notes. There is a relatively lengthy proof there for the divergence theorem. Okay. Yeah. So there's one little thing actually I wanted to cover. Okay. Before we go into the Stokes theorem. Okay. This example, let's call example here. This example I think is particularly useful for students going into the electrical program. Okay. Let's say I have an electric field, okay, for point charge. Okay, so you got a point charge at here. So here's a point charge, okay, at the origin. And what would be the electric field? And so that we can write it down. Okay, so that's your electric field due to this point charge. And I think you learned that probably in 178. Okay, yeah. And the R at here, okay, basically refer to any location, okay, any location in the 3D space. Okay, so this is your R at here. So R basically is the distance from that point to the origin. Okay, yeah, to the origin. Is that good? Okay. So first question is actually not really related to the divergence theorem. First question actually is about previous knowledge we learned. What do you think this del cross E to be? Del cross is a curl, but what do you think the value of this one? What type of field is an electrical field? Conservative. If it's a conservative, then del cross E must be 0. Okay, so you can verify it. Okay, it's 0, huh? You can verify it. Okay, so now I will do something like this. So let's say I have a sphere or some sort of a ball, okay, containing this charge at here, okay, containing the charge. So here's your surface S. If I'm going to calculate this surface integral, so basically calculate what is the total flux, okay, out of this surface S at here, right? You learn in your, I think you should learn in 178, there's a Gauss law, right? So what do you think these results will be? I'm not sure if you remember. It's what? So Gauss law says basically the net flux is basically the net charge, right, inside enclosed by the surface S here. So this will be equal to this, huh? Yeah. I'm not calculating, huh? You can certainly calculate this. So basically, say you have your vector field at here, plug it in. You have your n hat. Let's say any kind. You can use a sphere at here. Let's say consider this a sphere. You can calculate this, and then it turn out to be Q equal to over epsilon naught, the permittivity. As a matter of fact, it doesn't have to be sphere, and it doesn't have to be sphere. Any type of surface enclosing the charge. Okay, yeah. So that's pretty obvious. That's what you learn here. But now I want to confuse you a little bit here. Okay, I don't know if you. So now you can try to calculate del dot E. So I'm not going to calculate this. This calculation-wise, it's a fairly standard calculation. So you have your E at here, right? So substitute this one back over here. So each function, each component has a function x, y, z here, x, y, z here, each one of them, huh? Right? So if you calculate the del dot E, which is what? Basically partial m, partial x, partial n, partial y, and partial z, that 3 partial derivatives. Okay? That's 3 partial derivatives. Yeah. Is that good? Yeah. Now, if you calculate this one here, you actually will find it somehow equal to 0. Okay? Yeah. Now, I'm actually not gonna say the whole thing, but this is not exactly right. Okay, this is not exactly right. So if you calculate this one here, the results turn out to be 0. But however, if you remember, the Gauss law for del dot E is actually what? It's this one, rho equal to epsilon, and rho is the charge density. Okay, the charge density. Okay, yeah. So now this is the correct one, This is the correct one, and this is also correct. Okay, the calculation-wise, this is also correct at here. But what's the problem here? Why is 1 0, but then why is the other one is rho equal over the epsilon naught? Okay. The point here is, okay, so when you have a point charge, okay, when you have a point charge, the charge density, I don't know if you remember, the charge density is 0 everywhere except where? Except the location at the point charge, okay, at the point charge. So why I'm bringing this question is because you see here, right? So this is your surface integral results at here. Okay. Now, if you're tempted to say, why don't we just go ahead and use the divergence theorem to calculate this surface integral? Then what's going to happen? Let's try it, right? If I'm going to use divergence theorem to calculate this one here, so what I'm going to do? I'm going to basically calculate this triple integral, right? So basically, del dot E and then dv. That makes sense, right? That's your divergent theorem, okay? But based on the calculation, this one here, this is a 0, so this thing is 0. It's conflict, isn't it? Right? It's conflict. Yeah. So the conflict that here actually is because the one point I made at the beginning of the lecture. What is the condition that what is the condition that you can use the divergent theorem? What's the condition here? F needs to be continuous here. But look at this electrical field, right? The E at here. Is it continuous origin? No, right? So the origin is not continuous, and this surface S including this origin here. So you can't actually use divergent theorem at here for this particular case. That makes sense? However, if I give you a slightly different scenario, okay? Oh, the IT people probably is doing something. Okay, so let's come back to this question right here, okay? Let's come back to the question. If I change the question slightly, change the question slightly. So now the question becomes this. We have a region, which is basically I draw here two spheres. Okay, I draw two spheres. One is green, the other is the black one. The black sphere enclosing this the green sphere. Okay, yeah. So now if we consider basically the region, okay, between the two spheres. Okay. So basically for this case right here, okay, we have a region D. Okay, we have a region D at here, and now what's the surface enclosing this region D? The surface enclosing region D is what? One is this outside S1, this S, let's call it S black, and the outside, the other one is the inside one here is the SG, the green one. So there's a green and a black enclosing this region D, right? Okay. If I'm gonna calculate, let's say, so the S equal to S black plus SG. Okay, so two surfaces give us an enclosed region. And I'm trying to calculate what is the outward flux. Okay, what is the outward flux for this enclosed surface S? So that's sort of different, right? The previous one is just one sphere. Now I have two spheres. Is that okay? Right? So now the region D, you look at the region D here enclosed by this SB and SG. This region D does not include this origin anymore, right? So it doesn't include the origin anymore. So then you can use this divergence theorem. Okay, so in this case here, the divergence theorem applies. Okay, so now the divergence theorem applies. So you can use the divergence theorem here. You can calculate which this is 0. So this whole thing equal to 0. Okay, this whole thing equal to 0. Yes.
If the function is not continuous over the region of degree, then we have to do the hard way.
Yes, you have to do the hard way. Basically, calculate the surface integral as it is. Yeah. So now, what does this 0 mean, right? So basically, this side of surface integral is SB plus SG. So that equal to 0, right? That equal to 0. So what does it mean? Basically means the flux goes through this SB equal to the flux goes through the negative SG. I'm not sure if you recall, maybe one of the students actually asked about the cancellation when we were learning surface integral, right? I think this is probably what you actually, maybe in your mind, the cancellation, the situation here. Okay? Yeah. So in this case, basically, the flux goes through this B, okay, is the same as the opposite actually, the flux, our flux to the SG. All right, yeah. And the divergence, if you pick a point, right? If you pick a point inside here, that divergence equal to 0. So no sink, no source. Okay, so no flowing in, no flowing out. Okay, it's 0. Okay, that's actually quite special for the electrical field point charge there, right? But divergence, okay, the divergence is not 0 at the origin, huh? Divergence is not 0 at the origin here. Okay, it's only 0 other than the origin or the point charge. Okay. So you'll learn much more in your third year electrical magnetic field course. Okay, but this is basically the basic Gauss law in integral form, and then this is basically Gauss law in the derivative form. Okay. Yeah. Any questions? Okay. Good. So that'll bring us to the last theorem at here, which is the Stokes theorem. I'll write down a Stokes theorem at here, okay, and then we can take a detailed discussion into this theorem. Let S be a very smooth surface. bounded by a smooth curve C. Okay, bounded by smooth curve C. So I'll draw something in here. So basically you have a surface, and then it's bounded by curve C. So the surface S is in the top, and then this here is a curve C. Okay. So I'll draw the curve C out. Okay, I'll draw a direction for the curve C. Okay. Then if you're going to integrate over this curve C, basically this is what we call it. It's called the vector line integral, right? So if you're going to try to get the circulation, right? Try to get a circulation around the curve C. That's what this is, huh? Yeah. And this one is equal to the surface integral del cross F dot n hat dA. So that's Stokes theorem. This is one formula, one expression. Okay, that's Stokes theorem. Yeah. So let me go into the details of it here. Okay, so we'll explain, try to interpret it, okay, in a very easy way here. Okay. Again, if I look at the left side of it here, right? The left side here, typically we call this is a counterclockwise circulation. Okay, counterclockwise circulation around curve C. Circulation of the vector fields, right? So you have a vector field inside this 3D space. Okay. And then this side here. Okay, for this side here, so let's take a look at this side here. Okay. First of all, let's look at the integrand here, right? You have a surface integral. What is it integrating? It's integrating about what? It's basically, this is your integrand. Okay, this portion is your integrand here. So del cross F dot n hat. And if we just take it as a very direct appearances here, so del cross F is what? Is a curl, right? And then dot n hat. N hat, basically, if I pick a point at here, then this is your n hat. That's the normal direction to the surface S. Okay, and I'll touch actually right away at here. The n hat has to be compatible. The direction of n hat has to be compatible with the curve C. I'll write it down. I'll come back to this point here. But for now, let's just look at the expression here. So this is curl dot n hat. Okay, so curl dot n hat. Now, if you recall, when we learn the curl, how do we define the curl? We define, if you recall that, when we learn curl, we have a concept. I'm not sure if you recall that. What's the concept here? If you recall that, this is how we approached the concept of curl, right? So in that lecture, so we have this del cross F, the curl dot n hat equal to this. And what does it mean, right? Basically means, let's say for example, if I have like this location here, I can construct a very small curve delta C. Okay, very small curve delta C around that location. And n hat is the direction perpendicular to that small area, right? To the small area here. Okay. So So basically, this is the circulation around that little location, okay, and divided by the area, and then you let it equal to 0. So that, if you recall that, what do we call that? The circulation what? Circulation density, right? Circulation density. Okay? Yeah. So you got the circulation density. Basically, this quantity here, this del cross F dot n hat, is the circulation density at which location? At this location here. That makes sense? Right? And similarly, you can pick another location, and you can have n hat in this direction. Then you can get the circulation density at that location. Right? Okay? So then this surface integral here, what it says is, you integrate all of the circulation density over what? Over this given surface S at here. That makes sense? Okay? And what does it equal to? It equal to the circulation around this big curve C. That's basically what Stokes theorem tells you at here. That makes sense? Yeah. Curve C is the boundary of the surface S. Yeah, it's just the boundary, right? If you have a bow, then the edge is the boundary. Okay? Yeah. So that basically saying, if you want to calculate the line integral over the curve C, you can easily, or maybe not easily, but you can alternatively calculate the circulation density, okay, integrate circulation density over any curves, okay, that has this boundary C. Because why? You can easily obtain another surface, right, with the same boundary C at here. That makes sense? So you can essentially have infinite surfaces that share the same boundary C. Okay? Yeah. So this side here, I'll write it down here. This is basically integration of circulation density, okay, circulation density on surface S. So that's a connection right here. And superficially, it's basically a connection between a single integral and a double integral. Okay. Okay. So that's what this really basically the Stokes theorem is telling you right here. So I'm going to write down a few things right here. Another important thing is this n hat, okay, and this curve C needs to be oriented compatible or compatibly. Okay? Yeah. So compatible, I'll explain here, basically what it means is you need to pick your n hat appropriately such that its direction is compatible with the direction of the C. Okay? So here's what it means right here. Okay? Yeah. Here is basically what you need to use right hand rule for this compatibility. So this is basically what it means. Let's see, for example, I'll use this the drawing that I just draw there for illustration. Here's a curve C, right? Here's a curve C. Here's your surface S. If you orient your curve C counterclockwise by looking from the top, then your n hat has to be compatible. Use your right hand rule. So right hand rule, there are different way of using right hand rule because the surface S is bulged up, right? So this way here may not be that intuitive. So there is a way of doing this is this. So here's a C, right? Use your thumb, okay, pointing to the C direction, and then use your index finger. Okay, this is your thumb. Here's the index finger tangent to the curves to the surface S. So thumb is the direction C, and index finger is tangent, just sort of imagine it's tangent, right, to the surface S, and your middle finger will be the n hat direction. Okay? Yeah. So in this case here, well, you know what I'm saying, right? So tangent to the curve C, your middle finger is the direction curve C. It doesn't have to be very accurate. Essentially, once you do this, and you will see, okay, so my n hat must be pointing what? Must be pointing outward here. Okay, must be pointing outwards. Okay. So essentially, this will tell you what direction n hat you will pick. There are only two directions, either this way or that way, right? Yeah. If you not comfortable with this, you throw a coin, you have a 50% to get right. So let's see if I give you another curve, C and S, say here. Okay, so now this time the surface S is going down. Okay. So can you use your this right hand rule that we just learned to find out the n hat direction for the curve for the surface S? Yeah. So thumb is the direction of C. Index finger tangent to the surface S, and then middle finger pointing direction is the n hat direction. So in this case, where does it pointing to? It's going this way, right? It's going this way. Okay? Yeah. Yes. Yeah, go ahead.
So does it also work if you just throw your fingers around the direction C and then pointing to?
You could, but if you curve finger around the C, you get this direction here, right?
Yeah.
Your right hand rule. But that theoretically is not this direction for the surface S. That makes sense? Yeah. But it all pointing sort of the trend is the same. It's upward trend, right? Yeah. Now, as a matter of fact, remember what I illustrated here. How many surfaces share the same boundary C? How many surfaces share the same boundary C here? Infinite, right? What would be the one that is so special that has a boundary C? Which one has so special that has a boundary C? Which one? This one, right? The one that enclosed by the curve C, that's a surface. Okay? Now if you have the black one here and try to find the n hat direction for the black one, and this time the right hand rule is actually very easy. You do this, right? You can do this. What is it? Basically pointing this way here. Does that make sense? Yeah. As actually when you evaluate a surface integral and you decided to use Stokes theorem, if the question didn't tell you what surface that you're supposed to integrate over with, you can always choose a surface yourself, and chances are you may choose a surface that basically enclosed by the C. That's the easiest surface. Is that okay? Yeah. Unless the question specific said integrate this surface or that surface, right? Okay? Yeah. So this is the idea here. So I'll show you another one here, and then we can take a quick look at a couple examples here, right? So this one here is a little bit tricky, okay, than the other two. So this cylindrical surface is S at here. Okay, so this is a cylindrical surface S. Now, if you look at the cylindrical surface S at here, first question I should ask you is, what's the boundary for this cylindrical surface S? How many boundary does it have? It has what? This one here, right? So let's call this C1. It also had, sorry, I wouldn't draw it. This C1, and there's another one at the bottom here, C2. Okay, yeah. Now, if I want you to calculate the outward direction for the S, so I draw our direction n hat, right? Okay. Can you give me the direction for the C1 and the C2 based on the requirements for the Stokes theorem? Yeah. All right. What's the direction for C1, C2? Use your right hand rule. Yes. Alright, so try it, yeah, and then I'll show you what it is. Always remember the middle finger is n hat direction, right? And the thumb and the index finger is tangent to the surface, and thumb is the direction of C. So your upward C is this direction, and this one here is this direction here. Okay? Yeah. Now, when it comes to the Stokes theorem, so you have S set here, right? That's your Stokes theorem. So del cross F dot n hat dA. Okay. Now this time, technically speaking, you should add the two line integrals together, C1 plus C2. Okay. So for this one, and the direction C1, C2 should be the direction illustrated by the arrows set here. So the parametric equation, basically the parametric equation that you're coming up with for C1, C2 has to give you this direction, like this. Okay, yeah. So that's sometimes the tricky part, huh? Yeah. Okay. That's basically Stokes theorem. Yes. Pardon me? But you should know the right-hand rule. Usually, it's pretty obvious because your n hat essentially just two directions, right? And even if you pick the wrong direction, your results at the end will be just the sign difference from the right one, right? Yeah. So you won't get the full mark, but you shouldn't be too nervous about this. So you will get maybe 1 or 2 deduct, but otherwise you try your best to get the right. Okay? Yeah. Use your right-hand rules, or even use this right-hand rule, right? So basically that's your n hat. This curving is more or less in direction of a C direction here, right? Okay. Okay. So let's take a look at a couple examples that are here, right? Yeah. Actually, before we move on here, there's another tricky point. One of the students actually asked me in the office here. Okay, yeah. So the surface I showed you at here, it's an open surface, right? So basically, there is a boundary open surface. Okay, yeah. Now I want you to imagine this. What if it's not open surface? What if it's a spherical surface, like a ball, a sphere, right? What would be the boundary for that? So imagine this one here, right? Imagine this is the bowl at here. Okay? Imagine this is the bowl. And now your top is the surface, is the boundary, C, right? Now if I keep shrinking this boundary C, the boundary C getting smaller, isn't it, right? Keep going, keep going. when I fully close it, where did the boundary C go? It's gone, isn't it? The boundary C equal to 0. So if I look at the Stokes theorem here, if I have a closed C, which is a 0, what does this side equal to? 0. So the enclosed surface integral above this guy here is 0. Okay, it's a small trick here, but just think about it, right? Yeah. So that's sort of a topology here, huh? Yeah. This is actually, I don't want to confuse you. There's one formula to give it to you. I said the curl doesn't diverge. It's related to what I just illustrated it here. So let's take an example, huh? Let's take an example. Where you already, when you teach a new thing, you stick to the textbook, and you get used to the procedure of solving these questions. Here is a vector field y negative x, and z component is 0. S is half sphere. Okay, so this is your S at here. Now make sure that understand that this the red one is not part of the S at here. Okay. Let's calculate the line integral. Okay. Basically, here's your C at here. Okay, here's your C, and we want to calculate. We want to calculate this line integral. Okay. Line integral. If you never learned Stokes theorem and being asked to calculate the line integral over the curve C, then the first step that you have to do is to come up with a parametric equation for the curve C. Right? This parametric equation is the circle here, which is x squared plus y squared equal to 9. So the line integral, the parametric equation is 3 cosine t I hat plus 3 sine t j hat. Okay. Okay. And then you can use the typical approach for calculating a line integral, right? Basically substitute into here the dr and substitute x and y with 3 cosine 3 sine, and you can use your basically your t here because of full circle, so t go from 0 to 2 pi. Okay, so you can calculate this using the typical approach for line integral, right? Okay. Now I'm going to use Stokes theorem to calculate the line integral. Okay, so Stokes theorem requires the calculation, so I'm going to use Stokes theorem. So Stokes theorem says you need to calculate del cross f first. Okay, so let's calculate del cross f. Your f is over here, so this is just to calculate the curl of that vector function, and that can be calculated, which is negative 2 k hat. Okay, so it's basically the determinant of 3 by 3 matrix. Okay. So you get del cross f is negative 2 k hat, and then because Stokes theorem basically says this, right? Let me write down Stokes theorem again. So in this Stokes theorem here, the surface integral, you need the n hat. Now, in this case right here, as I said, there are infinite number of surfaces that share the same boundary C, right? So in this case here, I'm going to pick basically the S as indicated by this question. So this is your half sphere here, right? This is your half sphere. So I'm going to use this S, okay, for my calculation of the surface integral. Then there are only 1, 2, 3, 4 cases for surface integral, and this is a spherical surface centered on the origin, so I'm going to use that particular case. So basically your n hat is picked as 1 over 3 xyz. Okay. Those things are given for spherical surface. Okay. And your dA will be 3 square sine phi d phi d theta. Okay. Yeah. So now let's put things together. Let's look at this surface integral. What does it equal to? So del cross f is -2, so 0, 0, -2, dot this n hat, so 1/3 x, y, z. Okay, and dA is 3 square sine phi d phi d theta. Okay, all right. So that's the surface integral, okay, at here. Okay, let's calculate the dot product. So -2 over 3 z and times 9 sine phi d phi d theta. Okay, so the surface S. Okay, you don't want to keep the z at here. You want to get rid of the z using the spherical coordinates. And this is -2, so z is 3 times cosine phi. So that's your z, right? That's your z. And 9 times sine phi d phi d theta. Okay. And finally, you're ready to calculate the surface integral now by finding the limits for the phi and the theta. And a little bit simplification here, you get -18 cosine phi sine phi d phi d theta. Okay. The phi limits, you look at this one here, the phi limits and the theta limits are based on this given half sphere. So phi, you find the phi limits by looking at the angle between z-axis and this reading line. So starting from z-axis up to this location, so phi goes from 0 to pi over 2. And theta, then you sweep around the whole circle, 0 to 2 pi, so you get the whole scan through the whole surface. Okay. And here the integral here, you need a one step of substitution rule. Okay, and that's quite simple. So overall you get a -18 pi. Okay. Yeah. So that's basically alternative approach. Calculate this line integral using a Stokes theorem at here. Okay, Stokes theorem. It's hard to see which one would be computationally, in this case, easier or not. So whether that's less computation or this side is less computation. But I'll just give you an idea, basically. Okay. Yeah. Yes. Yes. If the f is conservative, it's still 0. Yes, of course. Yeah. Yeah. Yes.
So in the exam, we just did Stokes of the circle rather than the half sphere.
Mm-hmm.
Would that be wrong?
No, it wouldn't.
Same answer.
Yeah, same answer. Yeah. But unless the question specifically says integrate over this surface here, right? So if you insist on using this, you won't lose all the mark. You basically maybe a few points will be deducted. Just watch the question, what it asks for, right? If the question didn't say anything about which surface you're supposed to use, just use the Stokes theorem in general. Then you can pick any surface. You can pick this one for sure. Okay. Yeah. Is that good? Yeah. Actually, if you pick this one, if you pick this circle here, what will be the n hat? Okay, that's right. Okay. Yeah. That's good. It's actually easier. Yeah. Okay. Okay, so let's take a look at one more at here, and then I have a few more examples in the lecture, and then you can take a look at yourself, all right? Yeah. And we can maybe a quick reviews like this. Given a vector field, which is this, and inverted paraboloid, and a curve C at here. And apparently curve C is x squared plus y squared equal to 1. Okay. And we want to evaluate this line integral using Stokes theorem.
Is it 2xy or is that xy?
This one here? Z. Okay. So using Stokes theorem, again the question probably didn't, as I said, it's not specifically specified which surface to use. You can certainly choose your own surface, but I'm going to illustrate the idea here. I'll use the surface on the top right here. Okay. Yeah. First step, calculate del cross F. Okay. So ijk del is this. F is z, x, y. Okay, it's your cross product, right? And this will give us 1, 1, 1. Okay, I'll choose, as I said here, I'll choose this surface z equal to 1 minus x squared minus z squared. Okay, so I'll choose this surface. If I choose this surface for the surface integral, then first thing jumping in my logical is, okay, so which case does that corresponding to, right? Basically which formula that you should choose for the surface integration. And this is basically in the format of that explicit surface, so z equal to f of x, y. Then you can use that formula for n hat dA, if you recall that, right? There's n hat dA formula for that type of surface. But of course, you have to orient your n hat to be compatible with this C. And to use your right hand rule, your n hat will be this direction, okay, giving a counterclockwise curve C. And basically it's the upward direction, right? The upward. N hat dA, if you recall, essentially is negative fx, negative y, and 1, and dx dy. Okay. Right, that's your n hat dA for an explicit surface. We picked the positive because it has to be compatible with the counterclockwise C at here. So your f is given, and this will be basically 2x, 2y, and 1 dx dy. Okay. Okay, so once we get all of these things together, then we can put everything into the surface integral now. So 2x plus 2y plus 1. So the dot product, right? So this one here dot this one here, okay, is equal to 2x plus 2y plus 1 dx dy. Okay. And finally, you will try to find the limits for the x and y. And the limits for the x and y, so basically it depends on this surface, of course, but ultimately it's determined by what? By the shadow of this surface in the xy plane, and which is a circle, right? It's a circle. So it's a typical double integral problem now. Replace the x with 2r cosine theta, replace the y with 2r sine theta, and dx dy with r dr d theta. R from 0 to 1, theta goes from 0 to 2 pi. Okay, so double integral problem, and you'll get a number here, which is pi. Okay. So that's just illustration of how you can calculate a line integral using the Stokes theorem here. Okay. Okay. So take a look at the lecture notes. There are a couple more examples, self-study examples here. and that should be enough for Stokes theory. Any questions? Yes.
If use the other surface, it would be retrieved like a
Come again?
So it says if we use the surface of the other surface, we would have to do it to use other example, okay, that one?
Here?
Yeah.
Yeah, it really depends on what surface you're required to do, basically, right? Yeah. As I said, can you choose this circle as the surface? Yes. Oh, sorry, which one? Yeah, this one. Can you choose this one? Yes, you can certainly choose this one. It's actually probably easier, right, for calculation. Okay.
And in a final exam, would it ask to solve the problems here?
Yeah, the question could very specifically say use this surface, right, for the Stokes theorem.
It would ask you to use the surface.
Yeah, of course. Yeah, it will say that explicitly. Yeah. If it didn't say, it's up to you, right? Yeah, you can evaluate as long as you get the right answer, right? Yeah. Yeah. Answer is pi. Yeah. Okay, so I still have about 10 minutes here, so I can do a very quick review. Not really going to cover a lot of things here. Probably just sort of to show you a bigger picture, more or less like a mapping, for the contents that we learned since the midterm in here. So I'm not going to go with the order of our study at here. So I'm going to basically roughly use the contents and create a mapping at here. Okay. So after the midterm, so we basically have learned 3 types of integrals. We basically learned 3 types of integrals. Okay. And each type of integrals has a different way of evaluating it. The first type, so there's double integral function dr, dA, and then there's another one, triple integral, a function of single variable, and then dv, right? So, and in this particular case, if you think in your head, how do we evaluate the double integral? We can evaluate using either Cartesian or polar. And how do we evaluate triple integral? Cartesian, cylindrical, and spherical, right? Yeah. So you all have the formula there. So within this portion here, if you think about basically there is the question evaluation. There's also the question here when it comes to evaluation, right? Basically the process of finding the integral limits. So for each set of a coordinate system, how do I find the limits, right? You go through each steps, draw this line, draw that line, first contact, second contact, right? That kind of thing. Okay? Yeah. And of course, we have learned some applications, okay, based on the double and the triple. Typical applications including center mass, moment inertia, average function, weighted average, right? So those are the applications regarding the integrals here. So that's the first type. Another type is surface integral. Okay. So this one gives us the net flux, okay, through the surface. Okay. And when it comes to the surface integral, now same thing you need to think about, okay, how do I evaluate this integral? So there case number 1 to 4. So I separated the evaluation of a surface integral into 4 different cases. Basically, there's a planar case, a cylindrical, and then finally there is a z equal to f of x to y. Right? So those 4 different cases, and there are formulas associated with each one of the case. Okay. So when you are asked to evaluate a surface integral, and the first step is to ask what type of surface we're dealing with here. Right? You choose your formula appropriately. Okay. And then finally, there's another type of integral, which is the line integral. So this is basically a single integral now. Okay, so that's a line integral here. For line integral, or we call it circulation around the curve, say. Okay, so you need the parametric equation, right? So that's before the midterm. Okay, what's the parametric equation? And how do we simplify this everything, right, at the end into just a function of that parameter t or anything? Okay, so three-type integral. And on top of the three-side integral, at the end of the term, maybe the lectures in the last couple of weeks, and then we learned a few theorem, particularly maybe just two theorems here, or three theorems here. Okay. And the theorem will, what it does is basically connecting the integrals. Okay. It connects the integrals together. Right. So divergence theorem, so basically connects the double integral with the triple integral. Okay. So this is your divergence theorem. And basically, I'm just going to rewrite the divergence theorem right here, and right, it connects this double with the triple. Okay. And of course, the Stokes theorem, it connects the single integral with a double integral, right? Yeah. So line integral equal to the surface integral. Okay. Yeah. Now Stokes theorem. Okay, Stokes theorem. There's another theorem, right? What's the other theorem that we learned? The Green theorem. And what's the constraint for the Green theorem? The Green theorem deals with what situation? Deals with the situation in which plane? XY plane, right? Yeah. So as a matter of fact, the Green theorem is a special case of the Stokes theorem. Okay. So the Green theorem it's a special case. Okay, special case. If you replace this n hat with a k hat, and f is a 2D vector field, then it basically becomes the Green theorem. Okay. So I'm not going to write it here, but just remember, Green theorem is also a theorem connecting a single integral with a double integral, basically. Okay. Yeah. Now, if you think about it, this is basically on the top of the food chain. This is essentially what this course at the end of the term, what you learned here. Three types of integrals and two theorems. But at the bottom of the food chain, you have what? You have so many things, right? You have a dot, you have a cross, okay, and you have a partial derivative, and you have a parametric equation, okay. And then you have the gradient, you have the curl, you have this divergence. So those are all pretty much at the bottom of the food chains here. And of course, and there's also, as early as what we learned, lines, planes, okay, and maybe different type of surfaces. Okay, yeah. So those are all at the bottom of the surface. And if you think even earlier, from the first year, there are some integral technique that we have used consistently. Okay, substitution, integral by parts. Okay, so those are. So those bottom things serving as the nutritions to the top of the food chain here. Okay, yeah. So that's why I say for the final it's not comprehensive, but sorry, the final is not cumulative, but it's still comprehensive, right? Yeah. So you do use many of things here. Okay, so that should be it. And thank you very much for sticking out with this challenge course. Okay, yeah, and good luck with your final exam.